right, good afternoon, good morning, good evening. Welcome to the Topology Optimization webinar. Today we have a very special session dedicated to topology optimization in industry. This session is organized together with my colleague Matthijs Nangela from Delft University of Technology and Niels Agger from DTU Denmark. Topology optimization is now part of many computer-aided design programs, including Altair, Dassault Systèmes, Siemens, ANSYS, Camso, Autodesk, Diabatix, and Topology, SIMULIA, and many more, sometimes under the disguise of generative design. We have invited 3 speakers today based on our current network, representing major as well as relatively recent players in this market. Considering the wide interest as we see today, perhaps in the future we should organize another session. And today we have 3 wonderful speakers. Meanwhile, I saw Ming Zhou joined us. Thanks for joining on time. That's wonderful. We have the first speaker, Ming Zhou from Altair, the second speaker, Claus Pedersen from Dassault Systèmes, and the third speaker, Paul from Diabatix. We will start with the 3 presentations. In between presentations, we will not take questions, but we will leave all the questions at the end. And the presentation, ideally, between 12 to 15 minutes, that would leave us enough time for a lively discussion at the end. So, Ming Zhou, if you are ready, maybe you can start sharing your screen.
I can start. Sorry for a minute or 2 late. I didn't know I need to register, so I was looking for where is the meeting. Okay, I can start. Yeah.
As Ming puts on his screen, then a short introduction. Ming Zhou is from Altair. He leads the development of computational mechanics and design optimization solutions. He's a very active member of the SMO community, serving as the editor-in-chief of the SMO journal since 2020.
Okay. You see my screen?
Yes.
Let me put on presentation mode. Okay.
Wonderful.
Okay. Hello, everyone. Thanks, Zhou, for organizing this session. I think it's a great opportunity for us to kind of discuss about the progress, the evolution of industrial applications, and also exchange thoughts about the challenges and where the field should go in the future. So I just attempted to summarize some of the application growth over the last 20 plus years, and then I think at the end I will kind of give my own personal thoughts about where are the challenges, how we can go to the next step, and where lies the potential. So that's basically the outline I just mentioned. So if you look at some of the early applications that's around 2000 or before 2000, we saw applications at component level for, say, brackets, different types of brackets. Here's the engine bracket. This is also a bracket, and this is aircraft door hinge design. So those all showed great. Does it block? Okay. Those all showed great potential for weight saving. I think the rapid growth was triggered by Airbus application. So when they were designing the A380, there was a student from Denmark, Lars Krog. He worked at Airbus. He did PhD on optimization. So he applied topology optimization on this project, and it showed great potential. So they applied it on the leading edge ribs. So it's like 13 ribs on each side, and saved over 40% weight on these components. But not only they applied that, they published a paper that was very valuable, because if you don't publish, others don't see. And then Boeing took loads when they were working on, okay, let's, I can come back to that maybe. So Boeing took loads, and when they were working on 783, the Dreamliner, and it had a weight challenge. So basically they organized massively to use optimization, not just topology optimization, but it's part of it, to reduce weight of the design. And not only Boeing applied, I think it triggered through other supply chain. You know, aircraft design involves a very large supply chain, and Boeing demanded their supply chain to use topology optimization and optimization in general to for lightweighting. So that was, I think, an inflection point, if you will, that triggered more broad application. And then also at Boeing, during 357 development stage, they also deployed this optimization center models at Airbus. At Boeing, they had this big optimization center with a lot of engineers working on design optimization, and Airbus did the same during the 350 development. This is one concept study of a section of the fuselage, starting from topology optimization, how then you interpret and then complete it with sizing and shape optimization, basically. And then if we look at the application growth, there basically it grew across all the major industry verticals. Let me just check time. And here is an example of architects take topology optimization as a creative tool to kind of basically try to come up with new design concept for architectural design. And at Altair, we developed quite early on, we developed a process to try to apply topology optimization more systematically. You start with basically topology optimization to generate concept, then you create more low fidelity models like beams and joints and panels to do very rapid trade-off study, and that's what we call the level 2 concept. And then at the end, you use high fidelity models to finish the design with detailed sizing, shape, and so on. And this has been applied quite broadly today with different in different industry verticals. Here is an example that we were heavily involved with Ferrari when they developed this new generation of cars, and they really did the whole process with the C123 process. And so they were able to showcase this. And Daimler, they also applied the C123 on their new vehicle development. So then I think the additive wave came about 10 years ago. So it caught a lot of attention. I think that the additive manufacturing wave really made topology optimization more broadly known, because with the maker movement, it has a very broad influence, and topology optimization is seen as a perfect match for additive manufacturing, because now basically you can design complex shapes and then you can make them. And there was high dream that probably biomedical, this is an example, just concept proof example to showcase that you can basically design or maybe individualize medical implants with topology optimization going into then additive manufacturing, and you can design that for every patient individually. That's a dream. Then here I can show an example of BMW that's on their i8. It's a beautiful sports car. They use the open root connection, I think, of this in part, and production. So too many cases you can find for additive manufacturing components going into production. And the latest trend in automotive, we know that the mega casting is quite exciting trends, that you can now produce half of a chassis with this large casting components. Then it replaces parts that are made, like assembled with probably hundreds of components. So that's it saves weight. It also saves manufacturing costs. So I think Tesla pioneered the mega casting, and so like the Model 3 and Model Y's chassis are made in, I think, 2 or 3 sections of mega casting parts. Here is a Mercedes. I took this on YouTube, so that you see this is the mega casting chassis part. It's basically almost a full. It's at least 1/3 section of the chassis. That's their EV concept car, and so we've seen the journey. I think now it has reached quite mature stage, being applied across all major industry verticals. So the next trend includes, for example, going multiphysics, optimizing for flow and thermal performance. Here's just concept study on battery pack cooling channels. Later, I think my colleague will show some more interesting use cases. And so before I jump into the challenges, so maybe I can share some of my observations. So one of the observations is that the wave of additive manufacturing has come down. So we've seen at the height of the enthusiasm, many companies invest in that, but now I think they realize for mass manufacturing, it's probably not the way to go. So I think additive manufacturing is still relevant for sure, but the application will be pretty narrow on more specific high-value problems. For example, if you do a injection molding or casting mold, then designing and making the conformal cooling channels in a very complex way with additive manufacturing should be highly valuable. So I'm almost out of my time. Let me just say from my perspective where the future should go. So basically today, optimization is very broadly applied, including topology optimization, very broadly applied, and thousands of companies use this as part of their toolkit. But it stays with optimization experts. So I think our goal is to really bring the tool into the standard engineering process. So it needs to become the tool for every design engineers. So what needs to be done to reach that stage? So I summarize the challenges, the progresses we are making. So on the design quality side, basically, say structural integrity is the most important. So we made progress to cover not just compliance, but also stress that extends to fatigue. And there are successes, but also why I put in gray, these are areas that that still are work in progress, I would say, like how to effectively consider noise and vibration constraint, flow and thermal. And then you need to take care of also, for example, barcoding and large display nonlinearity. There research on that, but it still needs some more effort to get into the practical stage. And crash is another problem that's less solved, I would say. And then on the manufacturing side, we have great coverage for different manufacturing processes like casting and so on from geometrical perspective, but that doesn't necessarily consider the real manufacturing process. So how to connect with the manufacturing simulation needs to be also brought into the optimization problem. And then one of the big challenges, that's why it's probably the main reason that it says with experts, of course, they design how to really capture the real design. And then after you have results, it's a rough concept, and the design interpretation and geometry creation is a major challenge. For example, here, this is another large casting part replaces probably tens of components, but you can say the rip patterns is not you will get from topology optimization. How you create tools that can come out with a beautifully finished design interpretation, that is a challenge. And then go also from rough geometry to smoother geometry is another challenge. And then maybe trade-offs between design complexity, like here in the truss design example, that you can basically have a much simpler design that delivers very close performance. And then what ultimately we want to say is that the optimization process become integrated with the design norms of all major industries, like aerospace, automotive. They all have their own processes, and they all have their certification criteria. And only when you integrate that into this whole process, then it becomes a tool that every engineer would use. Just like in civil engineering, all the simulation tools are integrated with the design norms, and then interpretation should be automatically embedded, and then ideally you also want to offer trade-offs of different manufacturing options. And in the longer future, I think along the development of digital twins, that you basically would harness data from the functional usage life cycle. Those would connect back to the design. So basically that closes loop of design criteria, how you formulate your design. So these are, but that would be a much longer term future. Okay, sorry, I took probably too long, and let's hope we still have a couple minutes for discussion.
Thank you, Ming, for a great overview. So we will not take questions now, and we will leave questions at the end. Now
okay,
we move on to Claus Pedersen. Claus is Claus is the Optimization Technology Director for the Multiphysics and Multidisciplinary domain of research and development at SIMULIA Dassault Systèmes. He has also been a very active member of the SMO community for more than 2 decades, and today he's going to present some of the recent development of his group. Yeah.
Thank you, June. So yeah, when I got the invite, it was a little bit difficult to where should I start and end. I guess Ming had the same problem, but so I decided to take the electrical vehicle, and then I choose a few components here. So I decided to take a track rod, a steering nozzle, the antenna, and also a multiphysics optimization for the electric drivetrain. So I'm going to start a little bit just to tell where we're coming from. So I think like what a lot of people are doing is we're using the density approach. I'm not going into all the details here, but it doesn't necessarily have to be a linear material. It can also be elastic, plastic, or rubber. It can also be for motor reluctivity and for antenna design, conduction, electromagnetic. And then we are using like the joint sensitivities and some sort of filter to make the problem well posed and put in a regularization optimization problem. So I'm not going into many details here. So I think a lot of the technology have been around for a long time. But I think often when we read the academic papers, our world is a bit different, because we often have, like mentioned before, we have nonlinear tears. It could be geometric nonlinear tears. It could be contact. It could be constitutive nonlinear constitutive models like elastoplasticity. We have a lot of ties, couplings, etc. Always unstructured meshes, never structured meshes. Very big model running on many CPUs and many nodes, distributed memory. So there we have all the primal solutions, and that's actually here where I think we often ending up spending a lot of time on the joint sensitivities, because the complexity grows, like when we're using nonlinear static, eigenfrequency, steady state dynamic, or also implicit transient, which can either be Newmark or Euler, like these things. When you start implementing this one also in industrial setting, you still have all the constraints that you actually have to fulfill everything up the top before you can actually calculate the sensitivities. So here I think there's something we are of course working heavily on. I think other people also, but this is something where there's still a lot to be added complexity in here. So if I go to the track rod, there we actually want to, what was meant before, we want to look at the buckling here, because track rod is actually a device sitting in here. So this one should buckle at a certain load. So if you look at this green curve down the corner here, then the idea is that when you have a misuse load case, then it should start buckling. And so all the other components in this system are then staying untouched. And this buckling load should then be over a certain limit. And then this should also not be so when it's actually buckled, then actually everything doesn't fall into the ground. And then here we also have a requirement for the linear stiffness. So it's not a floppy arm when it's just under normal driving conditions. So that's also including optimization. And you will see here that we actually calculate over time here the reaction forces when it's buckling, and then we can then optimize for it. So here we have both quasi-static instead of static. We have geometric nonlinear tears, and we have elastoplastic in. And typically, if you just optimize, so what Ming also mentioned here is like when we start optimization, we'll then see that we'll get some void elements, we'll get artificial instability, it's a local buckling, and it's reported some early papers also here and later papers how to actually stabilize this one. But these methods were not that appealing to us, so we spent a lot of time to come up with an idea to here we see stabilize it, and we get the same solution to adding an element in some very recent publication we did on this topic to actually be able to address buckling problems in a geometrically nonlinear model. And now when we're adding this scheme, we can now do the full optimization and suppress this artificial nonlinear buckling. And what you see here is I just showed the initial design, and I showed the final optimized design. I keep all the void elements so you can see everything's round and stable in the deformation pattern. And you also see we get the design. But what's really interesting from industrial point of view is that we have to develop this stabilization scheme here to be able to actually do the optimization at rather few iterations. So we like kind of using 70 iteration here to fulfilling and getting this buckling behavior we want to have at the same time fulfilling the linear stiffness requirement. So this is something I think is still a lot of research also to make sure that the number of optimization iterations are fairly low, so you can scale it up to bigger complexity. So this was a design where I kind of tried to address like for buckling. And then I'll go into the steering knuckle. So we also see often this requirement for stiffness, in this optimization. So what we have done in a very latest paper from 2022 and 2024 in SMO is to try to address not component only for strength for stresses, but also include fatigue. So typically you'll have the car driving over some kind of load histories, and then we assume that the system is linear for the components, and we can superposition. So each time we can always calculate stresses. Then typically here we use people or industrial standard or certification will often be the Brown-Miller. So this is what is called the damage parameter. It can also be more advanced ones and simpler ones, but Brown-Miller is by far the most industrial standard. And there we have to use some different planes to find out where this one is the largest in each material point, because it's not there where we have the highest stresses. And then typically you'll do a rain flow counting to accumulate the damage, and that's what we did in the first paper. But in the second paper, we're looking at the fatigue reserve factor instead, and this is a factor. If this one is larger than 1, then we have then infinite life of this one. So I mean the component will sustain the lifetime. And this one here, if it's less than 1, then we have failure. So we're outside the endurance limit. So here we have the mean stress and the amplitude like a hiking diagram. And if you're inside here, then we are safe, meaning that the reserve factor is more than 1. I'm going a little bit fast over this. There's a lot of details, but if you look into the literature, you don't find so many papers on these topics here. And often components actually have to be certified and regulate against fatigue. So if I take this knuckle here, steering knuckle, so here I'm minimizing the mass. I have a requirement on the reserve factor should be more than 1, so it can have its infinity life. There are some displacement constraints on it, also for this for the stiffness. And then I have a benchmark, one where I just try to use stresses as a constraint instead, a stress constraint for misses, and then I compare it, and then I do the final validation, and then we see that this one is more or less 1, so mean that it will sustain, and this one is less than 1, meaning that it will break at some point. So this is also a topic that when actually certification process often include fatigue. So, but we don't see so many publications on it in the literature on this one topic. So I think that's an interesting topic also to look into. The next topic I'm going to address here in the car is the electrical machine. And the electrical machine, it's a complicated design process, as you see here. First, you do the layout, the motor, then you can make also a suspension system or hang it up in something, being topology optimized. You can look at the acoustic properties downstream, you can, etc. And then you have the entire control system. And this one here, we now want to optimize. So I'm looking at the first 2 steps, at the very initial conceptual design step, typically the step for topology optimization, as we know. And for the motor design, I will then look at the rotor. We can also look at the strata, both of them, but I'm just looking at the rotor here. And often we'll just make a 2D model. This is typically what you're also doing in verification processes. So we're kind of neglecting the edge effects coming out here from the electromagnetic. And also what is super important, this is one case where we're both looking at structural and EMAG properties, electromagnetic properties, but we also have to include the controller. You see this box sitting here. So this is the controller. This one we have to include because this is giving the difference between the voltages and the current. So the one coming in will impact the design because that one is also a design variable. You always have to tune depending on how the engine is driving. And here we have then also a moving mesh. So we have the electromagnetic properties. We want typically to maximize the torque. So we get a lot of power out, got a lot of torque out for the given power. But a very important thing is also we don't want a lot of noise in our car. So we have to suppress the torque ripplings. We can also use Fourier transformation and go into very specific frequencies. For optimization, I'm not doing this here, but it's something we often are doing also. And then at the same time, we also have this the structural requirement for stiffness and strength. So what we're doing here is that we are maximizing the torque output. For a given input, we have a constraint on torque rippling. We have our constraint for the electromagnetic. This one have the phase shift in here as a design variable. You see this beta between 0 and 90 degrees. It's basically like a bound, like what we use to 0 and 1 for the topology optimization. Here we have the reluctivity as a design variable, like this is the material properties. And you see here it's highly nonlinear. We have the stiffness and strength requirement using for misses stresses, and we have our equilibrium from the structural part. And here we then also have the magnets depending on how you have your assembly process, if they're glued or put in and etc. But I'm using contact here to it. So when this one is going 10,000 RPE, here to scale up, of course, you'll see the starting getting some openings in the contact. So then the idea is to then run the topolymization. So I'm using symmetry here. That doesn't mean that the engine have the same properties in the reversing and going forward. Maybe you don't want that, but this is what I have enforced here. And then you see the phase shift is also a variable coming out. So we also have the joint sensitivities that showed up front for the beta. We're maximizing the torque by more than 50%, constraining the torque rippling, stresses, compliance, and mass. So this here is but this is just a very simple example because in reality, you know, your car is driving differently. So differently, you will actually have different working points. So you can add a lot of complexity in here, cooling, acoustic properties, etc. So this here is, I think, we're just starting the surface or the journey here. So for these coupled systems, where we get not only a joint sensitivity for the material distribution, but also for other controlling variables, this is something I think in the future we'll see more and more of also, because things are actually integrated. Then the last thing I'm going to touch about the electromagnetic is the antenna design. So here we have the conduction. So before we had the reluctivity, but here I'm this one here. So the antenna is very small compared to wavelength. So today in these cars, you have many antennas and receivers, and they're very small. So the idea here is to maximize the far field. So you get a lot of energy out for your feet. You have your feet here coming in with certain frequencies, and then you want to get a lot of far field out. And then you have a constraints on this reflection coefficient. I'm just going to shortly explain what that is. So we see here the conduction get optimized. And that means that for some frequencies, when you come in with the current, you want this signal here not to pass at all, so don't get any noise in. And also for high frequencies, it should get nothing through here. And then in one given band, you want a lot of signal going through. And this, you see, then you want a lot going through here. So that constraint we have for the minus T dB, this is the one you see here. And this one is fulfilled also in the reconstructed design. And we say the far field. So this is just one example. And these ones can actually be integrated in the entire model because there can be reflection about it with other components with the antenna. So in reality, these antennas are never standing alone. You have to often to model everything around it. So then the last topic I'll go into is actually also what we saw in the other presentation. If I have my steering nozzle, and even though I'm optimized it for additive manufacturing, optimized for milling, I optimize it for casting and minimizing my mass, I have my constraints on stiffness and strength, then at the end of the day, I still have a density distribution, right? So what we have spent a lot of time with our fellow in the CATIA brand, is actually to be able to going from a density plot to a full parametric model, not an STL model or some dead, but actually a true CAT parameter with control points, etc. And this is kind of associative workflow, meaning all the load cases and everything you have over here, they are also automatically transferred and do very fast validation of your different design, but in a CAT setting. And that's actually super important if you want to get your designs out of living in a specialist group. You have to bring it back into your PLM system. You have to bring it back into a platform and integrate it so other people can work on with it. For example, what we saw before, like if you want to do additive manufacturing, you want to check if you can print it. If you want to be milling, you want to check all the milling machine can actually produce, etc. So this thing about getting the CAT in and getting the full digital thread on your component is actually important for acceptance in the as a component. And so what we also came to, here's the conclusion, just to address the latest thing we also published in SMO, was that often when we're down here, then people are working on the platform, they're doing different things and modification to it. And then they will say, okay, maybe I changed my loading by 10%, but you don't want to change everything in your design or something. Then what we decided was that we already have our density field, we already have our joint system, we already have the sensitivities. So what about if we use the CAT modeling in the density thing? So what we're doing is that we take our CATIA model or a CAT model, make it into a signed distance field. We make that into a density field, do a heaviside projection so it's cleaned up. And then we can then use our normal sensitivity fields. Then we go back with chain rules. And then, for example, we can have many, many CAT parameters we can then design. So here you see a small demonstration from this paper here. So we have our initial CAT model and optimized one. And here we have 16 design variables for the CAT model, but we're already using the densities in the background. So maybe a little bit more easier to imagine if we imagine we have this bracket here. So what you see here in this red one is the thing you're used to see when you're doing topology optimization. Here we have all our densities. So everything outside is 0, inside is solid, and then the CAT model can move. And here we have 74 control points in the CAT models and X, Y, Z, so 222 design variables. And then we can then go in and put some different loading on and do adjustments, or saying we did a very fast CAT reconstruction, we want to fine tune it now. And you can also put design rule in the manufacturing constraints in. So I think this is also a case like when, even though you have a CAT reconstruction, you still want to maybe fine tune a little bit. And here we try to use everything, what we already have from the density setting approach. So this leads to me like this last slide here. I think also what was shown so far is very much single components around, but in reality, we know that the components are actually interfacing. They can be in different positions. They can also be attached by nonlinear bushing, often for example in a steering system or in a driving system. There's a lot of bushing and dampers in. So in optimization, you also want, if you would do assembly optimization, you actually have to include these nonlinear features in between the components. This is a paper we did with Volvo in 2019, where we tried to show a little bit about how we include, for example, like the bushings in the optimization. So this is also a trend, I think, is that we see that components, interface between components are also optimized, like the stiffness of the bushing simultaneously with the topology optimization also. So also this trend again, like looking at more assemblies than just single components all the time. So I think that just leads more to conclusion. Hopefully there's more discussion. With electric vehicles, I think there's comes a lot of new interesting applications we have not really seen yet. Also with electromagnetic, we saw cooling before, but it can also be the performance, the acoustic of the machine. The joint systems are always very challenging to get it when you add complexity. How do you actually get a joint system when you're coupling physics? The thing about that to be able to actually impact to your colleagues, you have to go from CAT to CAE to CAT, and CAT is not STL file or something. It's actually a true parametric file you can put in and simulate on. So it's a part of your workflow digital thread. And also this thing with the multiphysics, that we're just starting to look at from the electric machines or high frequency application, where you can also have interaction between the structural, the electromagnetic, temperature you can also add in, etc. So here, I think this is also a topic which just started, and the complexities can also be extremely high, because the controller is also going to influence how your material layout should be. So I think with that, here I just say that I just touched some application here, but I hope that give an insight to there's a lot of challenging, interesting problem out there.
Thank you for sharing the examples, Claus.
Yeah.
Now we move on to our last but not least speaker, Dr. Paul Lacko. He's a senior R&D engineer at Diabatix, where he contributes to the development of topology optimization for thermal performance optimization. Thank you.
Thank you. So hello, everyone. Today, I would like to present the results from a case study we recently performed regarding topology optimization of a heatsink for cryogenic flow boiling conditions. But first off, allow me to introduce myself. I'm Paul Lacko, and I'm a senior member of the R&D team at Diabatix. I joined the company in 2021 after completing my PhD in mechanical engineering. For those of you who don't really know our company, in a nutshell, we aim to be the tool for every thermal engineer to help them along the way during every step of their design process. So we offer both simulation and optimization capabilities to design the most optimal cooling solutions for every application. Our optimization suite includes both generative design based on standard heatsink geometries, as well as topology optimization. Our core product is Coldstream, a generative design platform for cooling design. Coldstream is accessed through an easy-to-use online web interface, and there clients can define a case setup, upload geometry files, and specify what they would like to optimize. And from that point on, it's just a matter of clicking on the Run button and then returning after a few hours or days, depending on whether the case was a simulation or an optimization, to receive the results. Here are a number of optimized designs that we have delivered in the past. And as you can see, typical applications include both conjugate heat transfer as well as flow optimization for various material phases and physical conditions, such as natural or forced convection. So this has already been mentioned in previous presentations. We also place a lot of emphasis on manufacturability to ensure that our clients can produce the generated designs right out of the box. Most of our clients use one of the manufacturing techniques listed on this slide. So either a 2D manufacturing technique, such as CNC milling, die casting, or sheet metal forming, or 3D printing. The manufacturing specific input parameters are then just some of the settings that the clients provide when preparing their case. And these manufacturing parameters are then taken into account as constraints during the generative design process. So our clients thus receive fully optimized manufacturable designs as output, and an additional post-processing cycle is not required to make the designs manufacturable. All right, with that introduction out of the way, I would like to present a first case study, which we did approximately a year ago. The goal of this case was to boost the performance of a water-cooled CPU cooler. And to this end, we partnered up with Amnovis, an additive manufacturing company who wanted to get the most out of their 3D printing know-how. Together, we aimed to see by how much we could improve the cooling of a heatsink by using topology optimization and comparing to a conventional design. The image in the center depicts such a conventional design, albeit disassembled, and the sizing and specifications of this case are shown on the left and right, respectively. The optimization problem itself is actually fairly straightforward, with the goal being to minimize the temperature of a fixed flux heat source using a water glycol mixture and copper for the solid components. Further, there is a constraint imposed on the overall pressure drop, and this value of the constraint, 11 kilopascal, was set equal to the pressure required to operate the conventional design, such that we can make a like-for-like comparison between the two. The conventional design we compared to was a heatsink consisting of skived fins, and this is visible on the left on the slide. The fins measure 0.1 millimeters in width. This is not just some average performing heatsink, but really one of the best available on the market at the time. In comparison, the 3D printed design we generated based on topology optimization had features down to 0.28 millimeters in size. This value was, of course, determined by the minimum printing resolution. In this set of renders, you can see the fluid part of the Diabatix design. Essentially, the optimized design contains a flow distributor beneath the inlet, feeding very narrow channels to maximize the heat transfer, with the outer edge collecting the fluid and leading it to the outlet. Here, the temperature distribution on the heated wall is compared between the two designs using the same temperature scale. So simulation of both designs indicated that the optimized design was able to decrease the thermal resistance by 55% and increase the temperature uniformity on the heated wall by 80% for the same pressure drop. In addition, we ran a set of comparative simulations to typical conventional heatsink designs, so things like pins, fins, and TPMS-based concepts such as gyroids. And these results also confirmed the superior performance of the fully optimized 3D printed design. The nice thing about this case study is that the KU Leuven also performed several experimental measurements on our optimized design, and their results further affirmed the findings obtained through numerical simulation. So all in all, this case study was a great demonstration of what can be achieved when combining the cutting edge in manufacturing capabilities to state-of-the-art generative design. And now for the second case study and main focus of this presentation, this concerns the design of a liquid nitrogen CPU cooler. And for this case, we partnered up with Elmore Labs and Scatterbencher, two leading CPU overclocking specialists. The goal was to design a heatsink capable of sustaining very high heat fluxes, which would allow to further push the overclocking envelope. 3D Systems aided in the fabrication of the eventual design. Case setup-wise, it's actually relatively similar to the previous case study, in that the optimization problem was formulated as minimizing the temperature on a boundary with an imposed heat flux, and this boundary is visible at the bottom and represents the CPU. The peculiarities arise due to the flow regime under which this case intends to operate. So before I explain further, allow me to motivate the choice for liquid nitrogen as the coolant. So as we all know, CPUs generate a lot of heat at high processing speeds. In addition, for silicon-based transistors and chips, the thermal conductivity decreases with temperature. So there is an incentive to cool at lower temperatures. This makes liquid nitrogen an extremely interesting option as the coolant for two reasons. First of all, this coolant will evacuate the heat through flow boiling, for which it is known that the heat transfer coefficient is much higher compared to single-phase cooling, and hence there is the potential to efficiently remove high heat loads. And second, the evaporation temperature of liquid nitrogen is minus 196 degrees Celsius, which suggests that if we can operate the heatsink at this temperature, the thermal resistance of silicon will remain low as well. Hence, the main challenge with this case study was to capture the most important physical flow boiling behavior in the numerical model. We noted that under the envisioned operating conditions, three observations can be made. First, the heat transfer occurs under a constant thermal conductivity, since the 3D printing material is just one single material with approximately isotropic properties. Second, the heat transfer coefficient can be assumed to be approximately constant. Of course, there will be small variations within the pockets of boiling fluid, but these fluctuations are relatively small in comparison to the average heat transfer coefficient inherent to boiling. And third, since the phase change occurs at constant temperature, the far field temperature can also be assumed constant. So we used a homogeneous equilibrium model to model the two-phase flow. In such a model, the fluid and vapor phase are assumed to be perfectly mixed and in thermodynamic equilibrium. This allows the governing equations to be reduced to a set of one-phase flow-like equations. An additional equation is then introduced to capture and model the relative fraction, in other words, what percentage of the mixture is liquid and what percentage is vapor. The effective material properties of the one-phase flow are further also adjusted based on this relative vapor fraction. For the heat transfer model at the boundary layer, a correction factor or multiplier is applied to the single-phase heat transfer coefficient, and this correction factor is derived from two-phase heat transfer correlations. So, the reference design that we compared to is shown on the left. It is a design obtained through a combination of milling and drilling, and with features down to approximately 1 millimeter in size. On the right, the optimized design that Diabatix generated was based on 3D printing with a feature size of 0.8 millimeters. Again, this feature size was dictated by the minimum printing resolution. So 3D Systems was so kind as to manufacture a demonstration piece of the optimized Diabatix design for us, which was cut in half for illustrative purposes. And these cross-sectional flow graphs give us more insight into how the heatsink operates. You can clearly recognize a branching tree-like structure, which tries to simultaneously maximize the heat transfer surface area with the coolant, as well as minimize the solid conduction resistance from the base to the tips of the branches. The reference and the optimized designs were also compared experimentally by Scatterbencher in a sequence of tests. And this video shows the first test, albeit sped up, and it's basically a drag race to see which design cools down to the liquid nitrogen fluid temperature the fastest. So if we watch the video, we can see that both designs start at the ambient temperature, and then liquid nitrogen is poured over them. And while doing so, they measure the temperature at the base of the design, and the stopwatch is stopped as soon as the temperature of minus 196 degrees Celsius is reached. As you can see in the video, for the optimized design on the left, this took under 1 minute, whereas for the reference design on the right, this took 3 minutes to reach the same temperature. So moving on, the test results for all 5 experimental tests are tabulated in this slide. For the transient race tests, which were the first 4, our optimized design clearly outperforms the reference design in that it reaches the target temperature up to 3 times faster. And the last test also suggests that our design is more efficient, since for the same volume of coolant, the minimum temperature achieved is quite a bit lower. All in all, these results indicate that our generative design process also works for more complex physical phenomena and can deliver significant performance gains over conventional designs used today. In other words, there still is a lot of margin for improvement when we harness the potential of topology optimization. In case anyone is interested, here are a few links to publications and articles which discuss the case studies presented today in more detail. And with that, I would like to wrap up my presentation, and I look forward to the questions. Thank you.
Thank you, Paul, for the presentation. Now we have all the 3 presentations, and I saw on the chat we already have a couple of questions. Maybe we'll start from there, and meanwhile, if anyone have more questions, you could raise up your hand or indicate to me you have a question, then you can unmute yourself and ask. And for now, let's just go to the questions in the chat. The first question is to Ming. What do you think are the challenges preventing topology optimization from being adopted in many areas of manufacturing?
Yeah, thank you, Sophie, for the question. I think that's also what I tried to summarize at the end. I think there are 2 major challenges. How you can effectively and robustly consider all the design requirements. When you read a paper, usually it's a simplified problem, right? So, but when you deal with the real design, then you need to consider dynamic response and other requirements. And when you bring them into the optimization problem, often it doesn't necessarily work as you expected. And firstly, you have to have an efficient solution. So this is one challenge. But at the moment, I think the major challenge is design interpretation. I think that requires expertise and trial and error. I think how to go from the expert level to like simple toolkit for every design engineers. That's the major challenge. What I say is that now with the emergence of generative AI, I think it could help with, I think, both sides, how you package the design problem and then how you interpret the design and complete it as a really final design stage prototype.
Thanks, Ming. Then I move on to the next questions for Paul. It is about the gyro structure for CPU coolers. And the question is, did you obtain these structures, gyro structures with reverse engineering, or do you consider the use of gyros and then optimize the domain for better arrangement of these cells?
Yeah. So thank you for the question. In our case, it's the latter. So we consider the use of gyroids a priori, And then it's a matter of trying to figure out what the best sizing and arrangement is to place them within the design region to get them working most optimally. So that's what we refer to as our generative design.
And the related question is, does Diabatix, can Diabatix model nucleation boiling?
Good question. So far, the advances we have done on boiling are not at that limit yet, so we're not really able to model nucleation boiling. I think, as I explained during my presentation as well, we did introduce some modeling simplifications to capture the boiling process. So yeah, the answer to your question is no, not yet, but that is something we're working towards.
I will move on to a question to Claus. Claus, could you give us an idea of how the computational costs of the optimization vary from linear single physics problem to nonlinear multiphysics problems you considered?
I don't know. I had several ones. I don't know if that was the buckling one or it was the motor one. I don't know. But for the buckling one, we did new stabilization. We can run it pretty fast. But if you have a problem, depending on the problems, if you have a problem with a lot of bifurcations, like a lot of buckling points, like physically buckling points, then you have to take very small time steps in your back Euler or something to be sure you capture all things. So when we're doing aerospace buckling optimization, we have to be very sure that we capture each this one. So we are forced to take very small loading steps when we're doing that. So it's a little bit difficult to say. There will be a little bit like application where something just bending, buckling nonlinear might be very simple, and you hardly have any overheads going from linear to nonlinear. So this is depending a little bit like from application. So I don't know if I can give a general answer to that, but to give you a feeling, like everything what I showed here more or less was run on a simple laptop or a workstation. And also, if you think about more about the multiphysics with the motor, and you have more operation points, I think the motor took like less than 2 hours on a laptop to run, both for the structural and for the EMAG. But if you have more operation point, you have a cluster, of course, you can just run them simultaneously. And that's actually also, again, for nonlinear, is that I didn't show it here, but we have other papers we're working on with aerospace where we're submitting one where we actually show that you need a lot of imperfections because for buckling, also dressed is very complicated. What we talk about specialists is that you can have a lot of imperfections. It can buckle one way and it can buckle to the left, it can buckle to the right. So you have to consider these ones. And then you can run these jobs, of course, simultaneously, this one, but it costs you more computational cost. So maybe speed doesn't get up, but maybe your computational total costs get up because you need more clusters to run on simultaneously.
All right, thank you, Claus. Now return to a previous question to Ming. Regarding the C123 design approach you discussed in the context of vehicle design, could you please shed some light on what you meant by the low fidelity and high fidelity design in the second and third steps?
Okay, thanks, Richard, for the question. So basically, we developed a toolkit that's it has a quite easy to use interface environment. So the second phase, what we call the low fidelity, is that after you got the concept, you interpret the design, you build a simplified model, not 3D finite model. You simplify the car body into 1D elements and then some joints. You can also optimize the joint stiffness and panels. So with that, your turnaround is like a couple of minutes. So instead of hours. So then you can do thousands of quick design iterations for all your design requirements considered. We even developed the 1D crash model for crash simulation. So that way you can do very quick design iterations. After you finish that, then now you build your real high fidelity 3D finite model for the third phase to finish the design with the detailed sizing and shape optimization.
All right. So the next question is to Paul. The amount of topological details is dictated by the printing resolution. Could we consider the mass transfer limitation for controlling the topological details as well?
Yeah, good question. I assume the person asking the question is then referring to the boiling design specifically, and the mass transfer being the fluid transferring or changing phase to gas and being evacuated and having to be replaced by new fluid. At least that's what I assume. How I would understand the question. I think you make a good point, and I think that is something that could be considered in the future. It's not something we currently took into account when we did the optimization, because we more focus on like the steady state behavior. But yeah, given the fact that depending on how it's operated in how it's actually being used in practice, that could be an important consideration. And if you don't take that into account, then you might end up with a suboptimal performing design. So I think that is that definitely is something that could be looked at in the future.
Move on to the next question is to Ming. It is related to your the future work you mentioned. What innovation is by integrating digital twin concept with topology and structural optimization?
Yeah, thanks for the question. So I think the digital twin is one of the most fascinating development along with generative AI. So once you have the ability to connect to the real usage cycle of the product, harness all the data, now you get feedback from what is the performance and where are the issues regarding performance, what are the maintenance issues, what are the failure happening that's unexpected. So those could come back to your design formulation. So like I said, in order to go broad, you need to incorporate all the industry vertical requirements. And basically the digital twins feedback loop would give you a continued refinement process for your design requirements. So I think that's where it will go in the future, but that is a longer journey, I would say.
Now, I put a question there as well, just to, I really want to know, what do you consider, to all three speakers, what do you consider as the major difference between academic research and research in industry in the context of topology optimization? From the three presentations, I saw many projects could also be something at the university. So I'm curious about to know your think about it. Yeah.
Want me to go first? I can go first. Yeah, I think the difference is, I didn't go into too much detail. I think what Claus showed is industry research in the industry. You want to solve challenging real problems, and that is much at a different level, that you consider the detailed design requirements, what the product need to deliver, right? And from a solution perspective, I'm more talk about the solution perspective from how you can bring a toolkit to the engineer so that it's not being used by experts. What Claus presented is expert level usage. You have to go beyond that to make a bigger impact. That's my perspective.
So maybe Claus, maybe I can follow up then. So what I think is also like what I just briefly mentioned, but like people have modeling standard. If you go to Airbus or Boeing or automotive, like how do they do the spot welds, line welds, all these details, even though it's just designers, they have very simple rules. They have it in the pre-processors, in the post-processor, they can examine it. So there's never any voxel measures. There's never any just compliance optimization, so to speak. So, and these things. So if when you're starting doing very simplified tool, it could be a lot of work just bring it in to solve a few of these applications. So this to work very general is always a super challenge also for us, of course. So I think it can just be simple couplings, kinematic couplings, distributing coupling, like simple standard in aerospace and for certification, verification, documentation. These things are like minimum requirements, and you hardly see them, and people have a voxel measure and compliance measure, and then these things are not included. And for us, I think I spoke for all industries here, this is for us daily living, so to speak. Yeah, and we also see that this push that that we are a little bit fortunate. We have SolidWorks or CATIA, so also to put the tools into these packages that people are normally working with. I think that's a very big requirement also, because people don't want to leave if they're construction guys working in a CAD tool, maybe do a little bit simulation design. They don't want to do very complicated pre-processing, analyzing, and post-processing, but they want to stay maybe in an encapsulated environment they're used to working in and getting feedbacks. And that means that you have to integrate this solution also in the CAD tools or whatever they're working with in a daily basis. So we see that as a big requirement for people, because they cannot learn additionally extra 2 or 3 tools just for doing optimization.
Thanks, Claus.
Yeah, I think the two previous speakers already covered the basic idea, and I certainly agree to that. And mainly from my perspective, that, well, first of all, we as a company try to offer, simplify and provide an easy-to-use interface for topology optimization to our clients who don't necessarily need to be the experts anymore. But then the flip side is, of course, that similar to what the previous people already said, you do need to try to take into account their specific needs. So, for instance, manufacturability is a very important one. And yeah, that's where the primary focus is for us, is to make sure we cater to the needs of our clients. And also because I wouldn't say we're the same scale of company as the other two speakers here. So yeah, it's a lot more focusing on what works for us and what works for our clients, and less on really being able to, or getting the freedom to explore or really pursue the fundamental research as much, because of course it needs to be usable and ready for our clients and integrated with how they would further use it.
Maybe I can make a final remark. I think to especially to the young researchers in this webinar and the PhD students, I think it's an exciting time for our field. We've already seen real impact, very broad impact from topology optimization and optimization in general to engineering, that helps to improve products, improve efficiency, contribute to combat climate change. I think it's an exciting time for this technology to grow and to be broadly applied. Join the industry after your research, I think, combined with the wave of generative AI and digital twins, I think there is unlimited future.
Thank you. Looking at the time, we need to wrap up. Thanks to Ming, Claus, and Paul for these presentations and for the interactive discussion. We will have the next session at the beginning of December. The topic is to be decided. I will share the announcement in the topology optimization webinar and by email. So thanks for joining us today, and see you next time.